Okay, welcome back to Unit 9, Gas Laws, and in this section we will be talking about using stoichiometry and the gas laws to make chemical conversions. In the last unit we were able to convert moles of gas to liters of gas at standard temperature and pressure using 22.4 liters is equal to 1 mole. Well, how would you go about getting liters of a gas in non-standard temperature conditions? Well, you would use the ideal gas law equation. And so in the following pages, we will be doing that and using our knowledge of stoichiometry and putting it all together. Now, I think you'll find it not a whole lot more difficult than working regular stoichiometric problems. So let's get started on it. And we will be using the same flow chart that we have before in the past. And instead of using Avogadro's number, once we get converted to moles, we'll be using the ideal gas law equation. PV is equal to nRT. So we'll be able to predict volumes of gases involved in chemical reactions under varying temperatures and pressures. And here we have an example problem. And to save ourselves a little time, I went ahead and balanced the equation that we'll be using in the problem. And it reads here, how many liters of carbon dioxide, okay, so this is what we're solving for, liters of carbon dioxide, can be produced if 110 grams of hexane react with excess oxygen at 1.5 atmospheres and 30 degrees C. So you'll see here that we have instead of the standard conditions, STP, we have a temperature and a pressure that varies from that. And so let's get started and we'll write down what we're given. That's always a good place to start. We have 110.5 grams of hexane, C6H14. So we're going to go from grams to moles, moles back to grams, and then finally, moles to moles here, and then finally we will convert our molar amount to a volume amount using PV is equal to nRT. So we'll just rearrange that. Volume will be equal to nRT over the pressure. Okay. So, but first we've got to go from grams to moles. So grams will go on the bottom per 1 mole of hexane. And I looked that up for us. It's 86 grams of hexane per 1 mole of the same. And then we're here at the moles. So we'll have to go to moles of our new product. And so whatever you start off with always goes on the bottom of your conversion factor. So we'll have moles of C6H14 on the bottom. And then we'll have moles of our carbon dioxide on the top. All right, so whenever you go from moles to moles, use the balanced equation and the coefficients off of that. So let's pick off our carbon dioxide first. We have 12 moles of carbon dioxide for every 2 moles of our C6H14 or hexane. So when we do that calculations, it's 110.5 times 12 divided by 86 times 2. So here, now that we have our molar amount, we can use our PV is equal to nRT to adjust the volume for those conditions. So the volume here will be equal to 7.71. That's our mole amount. That's the mole amount here. Our R value is 0.0821 liters atmospheres, Kelvin mole. Those are units for our R value. And then we have a temperature of 30 degrees C. And 30 degrees C plus 273, remember you have to convert that to Kelvin, will be 303 kelvins. So you have all that as your top fraction, and you'll divide that by your pressure. We did R and T, and we'll divide that by our pressure. And our pressure is given as 1.5 atmospheres. Okay, so let's do the math there. And when we do the math there, liters of our carbon dioxide. Okay, so there's our final answer there. So these gas law stoichiometric problems are not any more difficult than the ones that we did before, but the main thing that you've got to keep in mind is that once you solve for moles, you have to plug it in to PV is equal to nRT to solve for either a pressure or volume or whatever they ask you to solve for. And the thing to keep in mind there is to watch your units. Make sure your units match your R value. Liters, atmospheres, Kelvin, mole. Now you can also do limiting reagent problems with these. And let's do an example of that. And so let's write down our balance equation. Let's see what would be a good color for that. Let's do that in white. I have to write in black there because we've got a white background. All right, so in this problem, we are given 45 grams of propane and 100 grams of oxygen, and we want to know how many liters, X in liters of the carbon monoxide that we can produce. So just like before, in any limiting reagent problem, you have to do a moles to moles conversion of the two reactants and figure out which one runs out first, which one is the limiting reagent. So you have 45.0 grams of C3H8 or propane, and you're going to go to moles of CO2. So if we do that, there's 44 grams. You have to use the periodic table to figure that one out per mole of C3H8. Use the molar masses to do that. And for every 1 mole of C3H8, we have 3 moles of CO2. Okay, so there's our part for the propane. Now let's figure out the oxygen. We have 100 grams of oxygen. Don't forget, oxygen is O2 here. So it'll be 32 grams of O2 per 1 mole. And then for every, let's see here, every 5 moles of O2, we have 3 moles of CO2. So we work those out. We get 3.07 moles here of CO2, and we get 1.88 moles of CO2. So it becomes obvious here that oxygen is going to run out first. So oxygen is our limiting reagent. And so we will use this value, the 1.88 moles, to plug into our PV is equal to nRT to figure out how many liters of carbon dioxide that we can produce. All right, so let's write that in red since we've got black and white backgrounds here. So here it will be volume is equal to nRT over P. So our N value is equal to 1.88 moles. Our R is constantly 0.0821 liters, atmospheres, Kelvin, mole. And our temperature here is given as 25 degrees C, which is 298 K. Should have that one memorized by now, right? That's a pretty common temperature. All right, and so all that over our pressure value here, and our pressure is given to be 1.3 atmospheres. So atmospheres will cancel, moles will cancel, kelvins will cancel, and our final answer will be in liters. And I believe if you do that, you get 35.4 liters of CO2. A lot of steps there, but very similar to the limiting reagent problems that we did before. Okay, so now we are going to figure out how to handle partial pressures. Sometimes you will have a gas mixture with different gases in it, and you'll need to be able to figure out maybe the total pressure of the gas, or maybe just the partial pressures of each of the individual components of the gas. And so there is a law called Dalton's law of partial pressures. And what it says is if you have a mixture of gases, that the total pressure of the gases in that mix is equal to the individual partial pressures. And so that's what we have here in terms of a notation. Here we have PA plus PB plus PC, and those are the partial pressures of gases. An example might be if you had A gas might be N2, and B gas might be O2, and C gas might be carbon dioxide or something like that. So the pressures of each one of those in a mixture equals the total pressure of the gas. Pretty easy concept to think about. And so To figure out these, you can do them with the ideal gas law equation, PV is equal to nRT. So in our example here, since we assigned A as N2, the pressure, partial pressure here of N2 would equal to the moles of N2 over RT over the total pressure, or I'm sorry, the total volume of the gas. So pretty easy a concept to get your hands around. The mole fractions of gases are often used. Sometimes if you have maybe the mole fraction or just the partial pressure of one gas, you can use those to figure out the other variables. And so the mole fraction, A, sometimes that's referred to as this funny kind of little X type of notation here, is equal to the moles of A over the total number of moles. This value is also equal to the pressure of that gas over the total pressure of the container. And let's do an example problem. There's all sorts of different kinds of problems that we can work here, but we'll just do one as an example to kind of give you an idea of how that might work. So it says here you had 1 liter of dry air, and it's 25 degrees C and 780 millimeters of mercury, and it contains just 0.925 grams of nitrogen plus other gases. So what is the partial pressure of nitrogen in millimeters per mercury, and then what is the mole fraction in mole percent? So let's see if we can work that out with our formulas that we have above. So let's write down some variables here first. V1 is given to us as 1 liter of N2. We have 25 degrees C, which is 298 K. And then we got a pressure listed. The total pressure in here is 786. So 786 divided by 760. Remember, there's 760 in 1 mole. And I believe when I did that, I got 1.03 atmospheres. So P1 is going to equal to 1.03 atmospheres. Okay. And then we're given N here in a tricky format. We'll have to change our grams to moles. So we're given 0.925 grams of N2. Nitrogen's 14 grams per mole times 2 give us 28 grams per 1 mole here. And that will give us a total of 0.33 moles. Okay, so to do this, we will figure out the partial pressure of N2 first. So let's do that. So the pressure of N2 will equal to the moles of N2, which we are given as 0.033 moles, times our R value, 0.00821. That's a constant, liters, atmospheres, Kelvin, mole, right? Times our temperature, which is 298 Kelvin. All that over our liters, which is 1 liter. So here liters will cancel, moles will cancel, K will cancel, and then our pressure of N2, when we work that out, is 0.807. Okay, so now it asks what is the mole fraction in mole percent? Well, we've got our pressure, right, of our nitrogen, and we've got the total pressure, so that will give us our mole fraction. Remember, the partial pressure over the total pressure is also equal to the mole fraction. So here we have our mole fraction here of this particular thing as 0.807 divided by the pressure that we're given as the total pressure, 0.03. If we work that out, we get a mole fraction of 0.78. 0.783 is the mole fraction, and the percent is just the percent of that represents, which is 78.3%. So there we go. We've worked that out. That's probably a little bit harder problem that you might have to work out. Usually they just give you some pressures and you have to add them up to get the total pressure, or they give you the conditions and you can figure out the pressures. So that takes care of the partial pressure types of problems that we will look at. It's more important to kind of know the concept here. Now we can talk about the kinetic theory of ideal gases. And we've already really talked about all these principles, but let's formalize them here a little bit. And the postulates are a way of explaining this behavior. There's 5 different postulates here. And like I say, we've really already discussed it, but I think now is a nice way to kind of summarize and formalize our knowledge of these ideal gases. Size of the gas particles are small compared to the average space between them. This is because these particles act as independent operators. They don't stick. They don't have very many or very little to no intermolecular forces. And so they are spread out, and the size of the gas particles is small compared to the area that they occupy. Gas particles are in constant motion. They travel randomly in straight lines in all directions and at varying speeds. This is important to note, that they're not all traveling at the same speeds, but together they have an average speed that is influenced by kinetic energy. And so when you put an amount of energy into the container of gases, they will reach an average speed that is related to the kinetic energy that's present. But each individual gas molecule will be traveling at different speeds. It says, therefore, here, factors such as pressure will be the same in all directions. And so that's the average pressure of the gas as well. The intermolecular forces between 2 gas molecules is negligible, except when they collide. That means that they have a speed that will be, they will have an untethered speed, I guess you would say, an unlimited speed until they collide or hit the sides of their container. The main point here is that when they collide, they don't lose energy, and they have a average speed that matches the energy or the kinetic energy that's present there. When particles or molecules collide, the collisions are elastic. They don't lose energy. It means that the average kinetic energy is constant. It depends upon the heat that's present there. The average kinetic energy of particles or molecules is proportional to the absolute temperature. The higher the temperature, the greater the kinetic speed. And so if you have a balloon that is increasing, that you have increased the temperature of, it will expand. The particles will collide on the sides of the container in relationship to the change in kinetic energy, or the change in temperature and the speed of the molecules in there. And if you cool it down, then the molecules slow down. They collide with the sides of the container less frequently, and the balloon will shrink. So in terms of volume and pressure and those types of relationships, it's very predictable, as we said before, because the gas molecules themselves are independent operators. They do not stick. They do not contract in size, and so therefore their relationships are very, very predictable. So this concludes our discussions on the kinetic theory, and then now let's talk a little bit about what happens when we have non-ideal conditions. And we call these things real gases, and I think that that's a little unfortunate that we call them real gases, because all the gases are real gases, and a gas can either have ideal conditions or non-ideal conditions. And if let's say nitrogen, for example, well, if nitrogen's in conditions where the temperature and pressures are quote unquote normal, or close to 1 degree, 1 atmosphere, and not super cold, maybe just regular temperature, it will behave and can be predicted by the ideal gas laws, ideal gas law formulas. But if you were to take that same nitrogen gas and you were to cool it down, and you were to create an extremely high pressure, then those gas molecules would slow down and they would start to stick, and then the ideal gas law equations wouldn't predict its behavior in terms of pressure and volume and all those types of things. And so we would say that it's become a real gas. And like I said, I think that's an unfortunate term. But any gas can be ideal, or any gas can be real, depending upon the conditions. So those gases are at high pressure and low temperature. So you condense them, you put them really close together and slow them down, and so they kind of stick. And so they do not follow the ideal gas laws. Predictions of variables cannot be made using these ideal gas law equations. High pressures and low temperatures, gases tend to be closer to each other, and then the intermolecular forces become significant. They start to stick together. That's how I look at it. Okay, these factors lead to a decrease in the volume that the molecules can travel, and a decrease in the pressure that would be predicted by ideal formulas. And then we use something called Vander Waals equations to predict their behavior. And that accounts for this decrease in volume and pressure that these gases exert. Talk a little bit about the Vander Waals equation. And this is a way of taking into or correcting somewhat the different interactions between the gas particles as you decrease the volume and you increase the pressure and the interactions between the gas particles. I have it written in a couple different ways here. One of the things that you should realize is that it relates to the original equation, or the ideal gas law equation, PV is equal to nRT. Notice here that the second part of the formulas for both are the same, but there is a correction for pressure and there's a correction for volume here. And this is because when the gases are compressed and cooled off, they get closer together, and so they're no longer dispersed so that they have free reign to move independently. They actually have some intermolecular forces reacting, and this Vander Waals equation is a way of accounting for that. The first thing that we'll talk about is this second part here, N minus V is equal to NB, and this is corrections for the reduction in volume. The N part is the number of molecules, just like before, is the number of moles of the gas, and B is a correction for the size of the different particles involved. And so you can look that up on a table. And so the volume is reduced there by a table value for each individual gas. It's a way of taking into account that now the size of the gas particles does make a difference in the calculation of volume. And then the second part here, I have it written slightly different than on the typed version. Either one is okay. But here we have a correction factor for pressure because of the decrease in volume. The ideal gas pressure is reduced by a factor, and this constant's determined for each type of gas. And this NV squared part of the equation is the concentration of the gas is in the number of moles divided by the volume squared. And it's squared because you have less frequent collisions, and they collide with less force. And so this correction factor is a combination of the intermolecular forces between the gas molecules, and that's very individualized for each one depending on the charge and the size of the particle. That's why you have to look that up on tables. And this N squared V is just another correction for the pressure part. So, we won't do any calculations with this, but it is nice to know that when you do have compressed gases at low temperatures, that you can have a correction factor available to predict their behavior. This kind of concludes Unit 9, gas laws. And it's been an interesting discussion of gases and gas behaviors, and I hope you've enjoyed it. We are almost done. We have one more unit left, and I look forward to seeing you in Unit 10. And keep working hard. Work the problems that I've given you in the examples. Try to find a textbook or online sources to work additional problems. These are the types of things that you can't really practice too much of. And as you're working the problems, think about the relationships and what's going to happen when you increase the temperature, what's going to happen if you increase the pressure or decrease the volume. So be thinking about the relationships as you work the problems, and be thinking about Boyle's law, Charles's law, Gray-Lussac's law, and the relationships between temperature, pressures, and volumes in gases. We'll see you in the next unit. Work hard. I know you will.